Hello, everyone. Today I'm going to talk about the topic. Hello, everyone. I'm Sorashite. I'm going to talk about the topic of a little clairvoyance is all you need. This is joint work with Anupam Gupta, Kaplan, Alexander Lindermayr, Jens Scholler. Let's get right into it. So this topic is about online scheduling problems. So the setting is that a bunch of jobs arrive over time and we need to process them. For each job J has it has processing time Pj. You need to do that until finished. Um, and then we consider the very simple setting. We have a single machine where preemption is allowed, meaning that you are free to switch to a different job and come back at any time. And the goal is to minimize the total waiting time, which is the summation of the completion time minus arrival time of overall job J. We are interested in competitive ratio of an algorithm, which is the ratio of the total flow time of the algorithm on instance J over the best possible algorithm, right? The optimal algorithm. Then we want to minimize this ratio. Ideally, we would love to get the constant competitiveness. Okay. And the key question in this area is that do we know the length of the jobs? Do we know the jobs processing time? If the answer is yes, then good news. So the shortest remaining processing time algorithm is an optimal one. So you can do it optimally, even in online setting. On the other hand, if the answer is no, we don't know the job processing time. This is called non-clairvoyant scheduling, meaning that the algorithm doesn't know the job length processing time. For example, the algorithm in this category could be doing round robin, right? You do every job at the same time, or the shortest elapsed time first. Unfortunately and unsurprisingly, that you cannot hope to get a constant competitive algorithm in this setting. The key intuition to keep in mind is that when you switch a job from job I to job J, then the adversary can ensure that you make a mistake in the worst possible way, right? Like the worst possible way is that when you switch to a different job, adversary makes sure that you have only very tiny left in remaining time. But because this is non-clairvoyance, you don't know. And that is the situation where adversary can take advantage. So given this very bad situation in this model, the next question is there more information or partial information that is helpful, that can help? And the answer is yeah, it depends on the model and in a situation. So if the partial knowledge is of the form that when a job arrives, I know approximately factor of two of the length, like we bucket the job length into some class, right? And then we receive the bucket number, the class of that job. Then we can have a constant competitive algorithm. Another model is that instead of giving a job length, we also receive the prediction, p hat at arrival. And then if the prediction is good, up to mu factor, then you can get a competitiveness that only depends on mu. But the key question in this area is that do we know the prediction? How do we get a good size predictions, right? If in particular, if you never touch on that job, how do you get a really good prediction from there? So another alternate idea on this question is that we should learn the size of the job when we actually start investing time on it, right? This gives rises to the model called the half Epsilon-clairvoyance. What does it mean? In this model, we consider that for every job J, initially the length of the job is not known to the algorithm, but once you process on that job for half unit of the remaining time, then you know the remaining time. Okay. So for example, when a job arrives, initially it's unknown, you keep processing it at some point, and then it becomes known, right? And then you know the remaining time because you hit the half of the total job, and then you can keep processing until you complete, right? So this model capture the motivation that you learn the job, like you spend half of the time of the job in order to infer or learn the remaining time, right? One toy example of this model is the research jobs or research projects as jobs. Because initially, if you're given a research project and you never start on it, it's very difficult to estimate how long will it take to finish. However, once you work on your research project at some point, when it is about to finish, you can estimate very accurately how long it will take it's gonna be done, right? So I think this model captures it. Generalizing from half clairvoyance, we can even define epsilon clairvoyance. So basically, instead of half, I just put epsilon in there between 0 and 1. Okay. And the nice thing is that this nicely interpolate between the two extreme, non-clairvoyance or like zero clairvoyance to one clairvoyance or fully clairvoyance scheduling. For the non-clairvoyant scheduling, we know that there's no competitiveness algorithm. There's no constant competitive algorithm. For the clairvoyance, we know that there is an optimal one, like very, very different. So the key question here is that how much epsilon do we need in order to get functional epsilon competitive, right? So do we live in the world that we cannot get constant competitive at all for any epsilon, or we are in the world where it could be constant at all at any epsilon? So the way to even like sanity check is to look at the previous lower bound of the non-clairvoyant algorithms. So the previous construction failed in this setting because when you switch to the job, adversary can no longer force you to make that big mistake. Like adversary, when you switch to a job, adversary cannot let the job to be very, very tiny. The remaining time of that job has to be a function of epsilon. So now we have some advantage. So the lower bound doesn't work. So our main result in this work, we show that positively for every constant epsilon between 0 and 1, there is a constant competitive deterministic algorithm. And in particular, we get this explicit function like the floor, the ceiling of 1 over epsilon. And then in the second theorem, we show that this is indeed best possible for deterministic algorithm. And for randomized, we show a also matching lower bound up to the constant factor, even for randomized algorithm. And more intriguingly, we also show the connection to the speed augmentation model in the non-clairvoyant setting. Namely, if you design a competitive Epsilon-clairvoyance algorithm, then there's a black box translation into a non-clairvoyance algorithm whose performance is a function of epsilon in the speed augmentation model. So when you define one model and it has a connection to the other model that is totally independent, this is like a good definition, like good mathematics. There's something interesting is happening here. All right, these are the main results that I want to mention. For the rest of the talk, I would focus on the half clairvoyant scheduling. This will make analysis or the discussion much simpler, and it will not change a lot in the analysis at all when you analyze the epsilon clairvoyance. First thing first, what would be the algorithm that achieves the main result that we have? It's a very, very natural algorithm. So let me explain. We call it SRF, which is the shortest lower bound first, and there's another name for it, which is the SRPT with estimation. The algorithm is this: you run SRPT, where if you don't know the length of the job, you pretend the length of the job of the unknown job to be the smallest possible remaining time that in this model. So let's imagine you work on an unknown job that you don't know the length for X unit of time on this job. The question is, what is the smallest remaining time for this one? If you consider this model, the answer is just X because X is possible, but you cannot go below X by definition of half clairvoyance. Also, the more you spend time on the job, the larger estimate becomes, right? So I can formally define the estimate as follows. So every job receives the optimistic estimate to be either the elapsed time of that job, if the job is unknown, or it is just exactly the remaining time if you know the length of the job. So we distinguish between the known job and unknown jobs. Okay. Now we can state in one line, right? The algorithm is that at any time I run on a job with the smallest optimistic estimate. Okay, let's say how it's gonna look like in the in the example. So in this case, let's imagine that we are given three jobs. Okay, we don't know the length of the remaining time at all, but we just mark here the dot the rectangle. Now initially, I don't know the length, so the estimate is zero. So basically, our will run on every job equally. And now the estimate will also go as the left time start going. And now algorithm will keep running. So the elapsed time will keep going up, right? And the red area represent the elapsed time, the amount of work that the algorithm has done. Okay. At this point, we reach half of the unit of the small job on the right. Then it becomes known. So you know the remaining time. So I denote the remaining time as green. Good. Also, um, in this case, if you think a little bit, then what will happen? Because in this case, the estimate are equal, right? But at the very small amount of unit, it makes sense that for the algorithm to run on the green part. Once algorithm run on the non-job on the green part, then the estimate become decreasing, and then you keep running on this job until finish, right? One crucial observation in this is that if the algorithm work on the known job, then it has to be the smallest remaining time. This is by definition also. But let's say that a new job arrived. I don't know the length of the job. What happened? This job will give a zero estimate, meaning that the algorithm will start working on this right away. So it will switch from the non-job to this job, to the new job, right? And then keep working on this. You have some elapsed time. It's still remaining very small until it will reach to the point that it's equal to the known remaining time. In this case, when the estimate here equals, then the algorithm will come back and switch and work to the known job and finish the known job. And also here is that now when the algorithm finishes this known job, now it come back and then look at the estimate, right? And now it work on the smallest estimate, right? Which is equivalent to the SCTF, like the shortest elapsed time first on the set of unknown jobs. One is become the same, it will keep running together until it hit the threshold, and then it becomes known, right? And then now you do SRPT, so you do finish one job at a time, and so on. So the key observation here is that you always alternate between the SRPT on the known jobs or SCTF on the unknown jobs. Okay, so let me briefly talk about the analysis technique. How do we go about this analysis? Okay, so the roadmap is that we have three steps to go. First, we're gonna define the classic technique for proving competitiveness and scheduling, which is the local competitiveness. Now, to maintain and then we prove local competitiveness by showing a mapping between the jobs in the algorithm queue and the optimal queue, satisfying the so-called 1-to-2 mapping property. Once we have this, we maintain inductively of this object over time, and then we get what we want. So first, let's look at the local competitiveness. So in this case, C local competitiveness means that I want to prove that at any point in time, the number of jobs in the algorithm is at most factor C times of the jobs, the number of jobs in the optimal queue. This will give us the competitiveness because you can integrate this local competitiveness over time, which will equal to the total flow time of the total waiting time of the algorithm, and then you get the competitiveness this way. So in the case of half clairvoyance, the main result is that the SLF algorithm is too locally competitive. Now, how do we show this tool competitiveness? We show by showing a mapping, 1-to-2 mapping like one to two mapping between algorithm and opt. So how do we prove the local competitiveness? Let me define this property. So we want to prove that at any point in time, there exists a one to two mapping between the algorithm and optimal queues. And the mapping is defined as follow. First, take the algorithm jobs in the algorithm and the jobs in the optimal queue. You build a bi-parallel graph between them. And then each node of the job, each node corresponds to a job where I assign the weight of the node as the remaining time. Okay. Now I order the jobs from left to right by increasing remaining time at this in this picture. So in other words, the mapping is basically just a fractional transportation or fractional matching in so to say. And we want this mapping to have the 1 to 2 property, meaning that 1 to 2 mapping means that it has the bounded prefix expansion. So when I say prefix expansion, it just means that for any prefix of op in this ordering, the expansion is never like the neighbor is never factor to more than the prefix size. So in this example, if you go to like the prefix of size 1, it never expand more than 2. If you go to prefix of size 3, it's also respect this expansion. So basically you have like 1 to 2 mapping in this way. So very good. And if we have this 1 to 2 mapping, it's not hard to see that you immediately get to competitiveness at this time. Because you can set this P in the prefix to be the whole opt, right? The whole job in the opt. And then we can get the local competitiveness immediately. Okay. So in this notation, N of P means the neighborhood of P, right? Okay. So the expansion is size 2. Very good. So I want to talk briefly on this why this is good enough for us to how can we maintain this? Okay, the easiest case is the job arrival. So imagine that let's say that I have a 1 to 2 mapping at this case. And suppose a new job arrives, right? It has size X. How do we maintain the new mapping? If you think about it, for 2 minutes, the answer is that you can just add an edge to this graph. And you can show that the prefix expansion is remains like still bounded by 2 because we just add an edge and that's it, right? So that's very easy to maintain. The harder, a little slightly harder case is the non-jobs. So if I have, so 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 we can say the following: I can maintain the 1 to 2 mapping if the algorithm is working on the known jobs. So the formal statement is the SRPT lemma. If the or processing time of if the algorithm keep working on the known jobs, then you can update to get a invariant. You can maintain an invariant. So in this example, suppose that algorithm working on a non-job. The key claim is that if you work on a non-job J has to be the smallest time, which is we have seen before. But up also is the SRPT, so it also has to also work on the smallest job. What happened is that in here, once you work, like let it run for 1 unit of time, then the suffix becomes, you can update by deleting the suffix, right? In this case, let's say that it runs for 3 more time units in this picture. You can also update it by just removing some mass of the node by 3, right? And then you can show that this is only a subgraph of the original graph, and then you can still have a good expansion. You can still have 1 to 2 mapping. Okay, so the hard part actually is the unknown jobs. So if you have a known job, we know how to update the mapping very easily. But when we work on unknown jobs, it becomes kind of challenging because you are update on the many jobs at the same time, and sometimes you alternate between known and unknown jobs. So this gets quite trickier. The main technical lemma or the main technical contribution of this work is to introduce this fast-forward lemma. Once we have this, then the rest becomes straightforward. So let me just briefly mention the lemma. So it says that if I give you a valid mapping, 1 to 2 mapping at time t, suppose a new jobs arrive right after time t, okay? and let t prime be the time such that the algorithm touches the largest job in the collection, while the collection becomes unknown. And during this interval t and t prime, if SIF never work on all unknown jobs, no other jobs arrive, then we can update the mapping at time t prime. Why this is useful? So let me show you why this fast-forward lemma can be used to maintain inductively over time. So briefly, so the goal is we want to show that we want to maintain the invariant, right? So let's say we start at time t0, we have this 1 to 2 mapping, a bunch of jobs arrive at this time. And then the idea is that we want to move forward to the next time step, okay? And then let's say that T star is a goal that we want to achieve show to show the local competitiveness at T stars. How do I move forward from T0 to T stars? So the idea is that we're going to define intermediate time step T1, and then we move to the intermediate time step, okay? And then the intermediate time step here I define as the largest T1 is the time for which the largest job in a new job becomes known. And then it could be that T1 can be less than T star or could be on the other side. But let's assume that T1 is less than T stars. In this case, we wish to apply the fast forward lemma. This one condition that we couldn't apply just yet because there are a bunch of jobs that could arrive during this time window, T0 and T1. The way we get around this technical issue is that we prove that we can actually adjust the arrival time of this job without changing the algorithm at time t1. So we call it early arriving lemma. So in a sense, we move those jobs and join the collection, and then now we can apply fast forward lemma and we make progress. And what happens if the job is too large? If T1 is if T1 goes after T start. Now, we're gonna use the define L0 to be the last touch time of the largest job. And so that we can start applying fast forward lemma again. And same thing, there could be a bunch of jobs arrive, but we apply the early arriving lemma, and then we can move forward. Right. So and then we keep doing this until we reach T1. So to conclude, we present the Epsilon-clairvoyance algorithm in this setting. It would be very, very interesting if we can also show this Epsilon-clairvoyance algorithm for non-clairvoyance for any other online algorithm or different setting and so on. What happens? We get a noisy estimate instead of true estimate at some point. It's also nice to explore the connection between 1 plus epsilon of speed and then epsilon clairvoyance in more general, in more different setting. This is what I want to talk today.